do some.
Yeah. Okay, yes. You know Grace Den? Mm-hmm. You know her, right? Yeah, so she was telling me you did that. Yeah, nice. Yeah. Let's see. Oh. Okay, woohoo! Alright, woohoo. Okay, so it's not exactly linear, but, okay. We're doing breath first search. Do you see a breath first search there? Who knows what breath first search is? You see it? Like, these guys are, S is the distance from S to S is what? 0, yeah. The distance from S to the next kind of level here is what? 1. And so on, right? That's the graph there. So we're gonna talk about that today. Okay, we're gonna compute shortest paths. Okay, show you how to do that. Also with weighted graphs. Okay, so and again, these are things you did in 61B, but we want to do them a little bit more carefully so you understand the properties well, right? You understand why they work and prove correctness and are able to change them around a little bit, maybe do something a bit different. That you see that on our homeworks. Okay, so okay, lecture in a minute. Okay, so the key in breadth first search is we don't use a queue. I mean, we don't use a stack. We use a queue because In some sense, it's very intuitive because what we put in first in the queue is the source, which has distance 0, and then we keep processing nodes in order of their distances from the source. And the source itself is at distance 0. So the queue keeps all the nodes at distance 0, which is just the source, and then from the source, all its neighbors are distance 1, and so on. Okay? So, and the ones who aren't neighbors of the source aren't distance 1. There's some distance greater than 1. Right? Okay, so you can, if you process them as you see them as neighbors of the nodes you process, you will get the nodes out in breadth first search order, or in order of distance from the source, and the thing that you need for that is a queue, not a stack. Okay, so Dijkstra is the shortest path in weighted graphs, and we're going to do this stupid trick of saying if you have a weight on an edge, we're going to change that edge into a sequence of nodes, a path of length equal to the weight on the edge, and then you can see that you can compute shortest path with breadth first search. Okay. And then we're going to say, well, we don't really need to do that. So I'm going to show you a little trick where you don't have to replace the path by the nodes in the middle. We're going to do use a data structure so you can sort of ignore the nodes in the middle. Okay, that you blow up the graph. Okay, and the priority queue, I'm going to tell you the priority queue implementation, which is degree D heap. I think you might have done this in 61B. Did you build a heap? Who built a heap? Yeah. Okay, so then the heap property is the children are larger than the parents. The minimum is at the top because, it should say children are larger than the parent, larger than or equal to. So then the smallest is going to be at the top, right? The parent is going to be smaller than its children, and their children will be smaller than their children, and so on. Okay? So we're going to talk about the complexity of each of these operations. Remove minimum element and reduce the key. And the idea is you're going to mess around with the tree a little bit when you remove the minimum element, because now you have a hole in the middle, so you have to deal with that. Okay? Okay, so, oh no. Okay, sorry. This is problematic. Okay. I only have the heap slides. Okay. Okay. Yeah, some people. Sometimes I get in a comment. The guy goes through like 800 slides in one lecture. That's a lie. It's only 200. I don't know what you're complaining about. But it's not really 200. I mean, it's like it's they're pieces. They're reveals. Whatever. Okay. So. Okay. Apologize. Control Shift P. Okay. Okay, we see this. Okay, so we're going to do paths and graphs. So what we want is we have a graph G, and a distance is the length. The distance between a pair of nodes is the length of the shortest path between U and V. Okay? We know what a path is between U and V. We're just trying to pick a shortest one. Okay? And in particular, we're going to think about this as there's a source, and we want to pick the distance to everybody else. So the definition is the source has distance 0 to itself, and the distance of any other node is the minimum over its neighbors of the distance of U, which should be a distance here, plus 1. Okay? So let's try, we have an algorithm. Let's try depth first search. Who thinks that's going to work? Nobody thinks that's going to work because, obviously we're doing a different thing. But do you think this will work? No, Professor, we don't think this will work. Okay, so in here I'm going to show you it doesn't work. I'm going to take S to be the source here. And this is a depth first search of this tree. And do you see a problem? Is node A distance 1, 2, 3 away from node S? No, right? Because node A is right next to S. It's distance 1 away from S, right? So clearly depth first search does not work. Okay? Okay, so so another algorithm is we're just going to pick it up. Okay? So we're going to think of these little things as sort of stringy things. And then we're going to pick it up by S. See, S is here. And look, if we pick it up, this is sort of what happens. Let's say we put a little charge on them so they spread out a little bit. And for some reason, they stay all horizontal. So now, does this work? Is this correct? I mean, are all of these at distance 1, and this is at distance 2? Is there a shortest path from B to S? Is there a shorter path? No. Right? So the distance from all of these to S is 1, because you can't be less than 1 unless you're S. And so B is really the only question, and B has no shortest path from S. So it's this leveling, right? So that's one algorithm. I mean, it's a little physical. You have this, you can see it again. There's the distance 0 vertices, which is S, the distance from S to S. Here's the distance 1 vertices, the distance from S to all of its neighbors is distance 1. And the distance 2 vertex here is anybody who has a neighbor at distance 1. Okay? So this is this recursive definition of distance. Okay? So we proceed layer by layer. And that's what I did. That's how I discussed it, right? So what we say is, well, what did I do? I looked at S. I said, oh, that's distance 0. Then I said the neighbors of the 0 node are the distance 1 labels. And so I write down 1 on them. And then after I look at all of them, I look at everybody who's neighbors of them, who are not already processed, and I write down 2, and so on. Okay? So when I do this sort of thing, untouched neighbors of the D nodes are D plus 1 nodes. So what happens here, this is distance 1, and now this guy D's neighbor is E. Now, it doesn't mean D's neighbor, E is at distance 2, right? It's only the untouched ones, right? We've already seen E. Okay, but B we have not seen. We see A's neighbor is B, and B has not been seen yet at distance 1, so therefore it's at distance 2. Okay, and if I said that all of these were at distance D, then B would be at distance D plus 1. Okay? So what data structure should we use to organize this? This lecture in the minute sort of messes up all my questions, but what data structure should we use to organize this? A stack. No, not the stack. That was just mean. Like I'm a little old and not always on top of things. So, yeah, of course the stack. No, it's a queue, right? Okay, so we use a queue. You do this whole visited thing again. It's almost the same algorithm as depth first search, except instead of using the stack or what we used there was the recursion stack, we're going to use a queue. Okay, so we set everybody to not visited, except for the source. The source is visited, right? We set its distance to 0, and we visited it, and then we put S in the queue. Okay, so now who's in the queue? Well, S. Well, what distance is it to S? 0. Okay? So only the 0 labeled nodes are in the queue at this point. Right? Okay, then what we do is we pop Q, and then for each neighbor, for each edge, from whatever vertex we pull out of a queue, we look at all its neighbors, and if their neighbors are not visited, this is what I mean by untouched, then we we say, now we've seen you. And we set their distance to 1 more than my distance, V. Yeah, distance to V is a distance we already know for U, right? Because U already has a distance because it's in the queue. So it's a distance to U, which is a distance labeled to U, plus 1. Okay? And then we put V in the queue. Okay? So the nodes are sort of explored in order of distance from S. Okay, when they're in the queue, because the next one that's taken out is not necessarily this one. When will we take out a D plus 1 distance node? After all the D ones, right? Because the D ones are already in the queue, like we saw it before. Okay. Okay, so while node U is in the queue, you add the unvisited neighbors of U to the queue. Okay, so you pull a node out of the queue and you add the unvisited neighbors of U in the queue. That is, in words, what the BFS procedure does. Okay, so the inductive statement is that the queue at any point in time only has distance D and distance D plus 1 nodes. Okay? That's what we're going to say. Okay? When all the distance D nodes are explored, the queue has all and only the distance D plus 1 nodes. Okay? So we're going to argue these statements inductively. Okay? S is explored first. All its neighbors are in its queue. The first thing you do is you put S in the queue. You pull it out. Nothing's in the queue. You explore all its neighbors. And what after you explore all its neighbors, what's in the queue? All the nodes at distance 1. Okay? So this is true. This statement is true for D equals 0. Both the original statement, Q only has distance D in 0 and 1 nodes. It only has 1 nodes in this first iteration, in this base case. And after you explore S, all the distance 1 nodes are in the queue. That's a 0 plus 1 is 1. That's a D plus 1. Okay? So D plus 1 node has a distance D neighbor. Right? That's the definition of being at distance D plus 1. The minimum over your neighbors of their label plus 1. Okay? So any distance D plus 1 node has a distance D neighbor. Right? So that's the definition of distance. So when the last distance D node is explored in the queue, now what you've done is you've processed all the distance D nodes. Right? So it tells you that anybody who's at distance D plus 1 must be a neighbor of one of those. So it must be in the queue. Right? Okay. So every node at distance D plus 1 is, well, it may not, maybe it was visited at least. At least you look at it. And either you put it in the queue or it's already visited. So the queue has only distance D plus 1 nodes. Okay, now it has no bigger nodes, right? Bigger than D plus 1, because you haven't processed any D plus 1 nodes yet. Okay? Since you haven't processed, you've only processed nodes less than D plus 1. And none of those, anybody at distance D minus 1 does not have an edge to anybody at distance D plus 8, because otherwise that guy's distance at D plus 8 would not be, if you have an edge from a D minus 1 to a node, its distance must be D, not D plus 8. Okay. So it has no nodes labeled larger than D plus 1 because you haven't processed any D plus 1 nodes. And moreover, it has none that are less than D because you've already removed them by induction. So the only vertices in the queue are at once you process all the labeled D or distance D nodes, there's only D plus 1 distance nodes in the queue. Okay? Okay, so this tells you we have this inductive statement and says, then the algorithm basically, it tells you, by induction you're going to work, right? Every time you label a node now you have to go back and look at the algorithm and say, every time you put a node in the queue, you label it with properly. And that's just what you do. Okay? You label it one more than its neighbor. Okay?
Excuse me?
Yeah.
Could you explain more why it has all distance D plus 1 nodes and not just only D plus 1 nodes?
It has all of them because, why does it have all of them? Because we know they're all visited by this time because we've processed by induction all the distance D nodes. So we know one of their neighbors is processed. Okay? So now when it's processed, what that neighbor will do is put it in the queue. And that's why it's always in the queue. Now, the only way it could not be in the queue is it was already visited previously in a previous iteration, right? But then that means it must have been visited by somebody whose label is less than D. And if its label is less than D, and you have a neighbor to it, it's not distance. Okay, what am I saying? Okay, so okay, so this is going to be kind of janky. So let's try it. Because, yeah, I'm getting consulting on my computer. So, oh, wow, look at that. Okay, so, okay, there's an edge. Okay. That one, okay, that is distance D. What is this? What's the distance to that? No, it's less than or equal to D plus 1. Okay? Okay? So now, okay, so there's a board, but, okay. Okay, I know how to do this. Okay, there you go. Maybe I can do it this way. Okay. No. Okay. Sorry. Okay. So what I'm saying is that you had all the, let's think about it this way. You had all the distance D nodes in the queue at some point, right? That's what the inductive statement says. Right after you processed all the D minus 1 distance nodes, you have all the distance D nodes. Okay? Now when you haven't seen any D plus 1 nodes yet, right? Because you only process D minus 1 nodes. So now when you process a D node, you're going to put the D plus 1 nodes in. Now where are you going to put them? At the end, because it's a queue. That's where we're using the queue property. That's a good question. Like if we put it somewhere in the middle, then that would be disaster. Okay? That's not a queue. But since we have all the D nodes there, all the D plus 1 nodes will be after them. So when we're done with all the D nodes, then we start with the first D plus 1 nodes we process. That's all the D plus 1 nodes. Okay? Okay. Okay, so okay, so breadth first search, we can watch it, I guess. I don't know. This is exciting, I guess. Okay. Okay, we're putting the node S in the queue. This is the graph we did before. Now, what we do is we pull S out of the queue. We labeled S0. We pull S out of the queue, and then we start labeling its neighbors, right? We visit E, and we visit all its neighbors, D, visit A and C. Look, all the numbers are 1s, right? They're distance 1. Okay? So now what we do is we pull E out. We look at D. D is already visited, so we do not put it in the queue. Okay? And then we process C for some reason. I guess it's in some arbitrary order. So, and then we process A. We pull it out. It has no neighbors. Oh, it has B as a neighbor. Okay, when we pull out A, we pull A out of the queue, so it's no longer in the queue. So we're processing A. Now A has a neighbor, B. Okay, we haven't visited B, so we put B in the queue. Okay, and then so on. And now we only have B in the queue, which is all the D plus 1 nodes, and that's the answer. Okay. And then finally, that's when we process C. This red edge, we're processing C. It looks at its neighbors. It sees that B is already visited, so it doesn't put B in the queue. And then it pulls B out of the queue, and it's done. Okay? B sees that both of its neighbors are visited, so it doesn't put them in the queue. Okay? Okay, so that's breadth first search. Okay, so now what we want to do is actually do driving directions, right? We want to go from between these cities. Okay, now, here it's like, say we want to go from San Francisco to Los Angeles, you just go on I-5, right? That's just one road, and you get there, right? So it's one hop in this particular graph. So breadth first search would work because there's only one length one hop here. So just do breadth first search, and then, well, now you can write down the distance if you want. That is the shortest path. That's one hop, shortest path, right? But you can quickly see that the breadth first search is not the right thing. You don't want to minimize the number of roads you traveled on. You want to minimize the total distance you travel. So this is good. I'm going to show you this is nonsense, but you already know this is nonsense, right? There's this two-hop path, which, the shortest, the fewest number of roads to take between San Francisco and Las Vegas is we can compute using breadth first search. And there's a length. There's something with 2 roads, but that's not the shortest one, right? There's a shorter one, right? I think there's a shorter one, right? This is, there's a longer one, okay, which is also 2 hops, right? So maybe breadth first search returns the longer one instead of the shorter one. So this is like a really bad algorithm once you have weights. You want to actually pay attention to the weights. And obviously, from Reno to LA, somehow here's a 2-hop path, which is much longer than a 3-hop path. So breadth first search is just the wrong thing here. It's almost the wrong thing. Okay? Can you make it the right thing? Okay, so this is this graph. Now you have numbers on them. Now the shortest path from S to E is not 7. That's just 1 hop, right? 1 edge. But it's clearly this is a shorter path, right? From S to A to B to E. So can you kind of think about how to change breadth first search into something that can work on this graph, or change this graph so the breadth first search works? How would I? Yeah. Yeah, he says use a priority queue. He's jumped ahead like 4 slides. So that's right, but it's not what I want. Something a little simpler. Yeah, what's Yeah, so what you can do is, what he said is to change this edge into a path of length 3. Right? You put 2 vertices on here. Okay, and what do you change this edge into? Path of length 7. Right? 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 So this one is a path of length 1, so it doesn't get another fake node. So we just make a bigger graph. Right? This is fine. This works. And now can we use breadth first search? Yeah, see, we can just use breadth first search. Well, S, you put in S, all the guys at distance 1, all the nodes, vertices at distance 2, and so on. Right? And you see that something funny happens here, right? There's these unexplored nodes here. We don't care once we label all the real nodes, vertices. Okay, so here's this really trivial sort of thing. Yeah, of course, with breadth first search is actually very powerful. You can just change any problem with integers at least and change it into a different graph where it works, right? And clearly it's correct because now the shortest path is a path. You're still finding the shortest path in this graph, which corresponds to a path in the original graph, and it corresponds. They have the same length. Okay, any path between 2 of these nodes. Now the length of that path includes the length of the weights. Okay. So the correctness is trivial because we just did a reduction. Okay. What's the time? What's the sum of over the edges of the length of the edges? Right. This is what you have to take this graph and you have to modify it in this way. Okay. So it can be problematic. Like here, what's the shortest path from A to B? It's 1,000,000, but it's 1 edge, right? We know it just jumps out at you because there's only 1 path. There's 1 edge, okay? So this is a trivial problem to solve. But the breadth first search algorithm will take 1,000,000 time units, right? You would build a graph that's the size of 1,000,000 and you do something really stupid and do this breadth first search, right? So it seems not good, okay? It's obviously 1,000,000, right? This is like, this is lame, this way of doing it in some sense. Could be easier. Okay, so let's think of this lame way of doing it. What are we doing? What does breadth first search do? It's trying to compute the distance from A to all these other guys over here, all these other vertices. Okay, so what does it do? What does breadth first search do? It does this. It does that. It does that. It does that. It's just painfully slow. Oh, please. And it's kind of doing something a little stupid, right? It's not doing anything. It's never seeing a real node at all, real vertices at all. It's only like playing around with these dummy vertices, right? And in each one of these edges, what's happening now is that red node is going to queue the next node on that same path, right? It's not doing anything interesting in some sense. It just queues the next node on this. It's just nothing is going on, right? And you keep going, and you're like, it's so boring. You see that guy yawning? Yeah, you. Yeah, it's really Get back to me in 20 steps. That's what he says. Get back to me when you have a point, man. So, and the point happens. Here, there's a point is made when you get to C. Right? Then something interesting is happening. You're labeling the distance to a node that you care about the distance to. Right? Okay? So all you need to do is just put me to sleep and wake me up when something actually interesting happens. Right? Like when C gets discovered. Okay? By this... Okay, so what we're going to do when we want to be woken up is we set an alarm, right? So we have this process. We set d of a to be equal to 0. When will C be reached in this time? When will it be reached? At time what? 20, in the 20th step. Okay? So what we do is we're going to process A, and what we're going to do is we're going to set some alarms. We're going to set an alarm for C. For the edge EC, what we're going to do is we're going to temporarily label this as 20. It looks like it's about 20 away from me, but I'm not taking it too seriously. And I'm going to set alarm for 20 units from now. Because I know what breadth first search will do is in 20 steps it will get to C. Okay? I might get to there before that, but maybe at most 20 sets it gets to C. Okay? Because it's a neighbor, I see that it's only 20 away. If I run breadth first search after 20 iterations, 20 units of distance, I will get to C. Okay? Or maybe before. Now, what about for the edge A to B? Okay, so you look at all your neighbors and you say, look, if I just run breadth first search, when would I get to B? In 20 time steps. In 20 sort of units of distance in breadth first search. Yeah. It might. Well, I'll show you. Okay. So we're going to get to B in this algorithm faster than in 30 steps. Do you see why? Okay. Everybody see why? So this is sort of an upper bound, the alarm right now. Okay. So what I'm going to do is I'm going to give you an alarm algorithm that behaves the same as breadth first search. Okay. So right now, I know when's the earliest time anything happens. Next, at time 20, right? Nothing's going to happen because I have an alarm at 20. I'm going to set an alarm for 30. I don't have to do anything for 20 steps. 20 passes through distance levels, right? Okay. So at time 20, I'm going to say, oh, okay, the alarm goes off. And I'm like, oh, okay, what do I need to do? I need to, take a shower or something, but also process C, right? That's what you do in this alarm. Okay? So now what do you do when you process C? Well, you look at C and you say, look, I have a neighbor D, and I see that if I ran this breadth first search time algorithm, I would get there in 23 in 3 more time steps. So I set its distance to 3 more, right? Because that's what breadth first search would do. And I set it to 23. And I set an alarm for 23, time 23. And I said, wake me up at 23. Okay? And I also look at this edge C to B. Okay, so now what I see for this edge to C to B, I saw that its old distance label was 30. But now I see that, wait, for me, I can get there. My distance is 20. This edge length is 4. So I can reset this time step distance to 24. Okay, and now I see that the old alarm was 30, so I need to reduce the alarm. I need to actually do something at time 24. Okay, so I set the alarm for time 24. And then from there, at time 23, what do I process? Right? What do I process at time 23? D, right? Why did I wake up at 23? I set an alarm at time 23. So at 23, I didn't do anything at 21 and 22. I was sleeping. But 23, an alarm goes off, and I have to do something, right? And that's process D. And then you see set D to be 23, and then you process the neighbors. Right now, what you have a distance label on B of 24, but if you go through D, you have 23 plus 3, which is 26, which is larger. So you don't reset the distance there because it's bigger than the distance you already know. Okay? So you leave it. D of D is 24, which is less than the distance to D. And then plus 3. Okay, so at time 24, you process D, B, and you're done. Okay? So, look, this looks like a mess, I grant you. But we didn't do much, right? Like compared to the previous slide, we're doing these nodes and these nodes and these nodes and these nodes. We only did anything when we actually processed a real node. Okay? So the work here is only proportional, sort of the work you do on real nodes. Okay? Not these fake nodes. Okay? They're just sort of an analysis trick. Okay? Okay. So, and now you're done. Okay. So what needed to be done? You need to set a distance. Okay, that's what one thing needed to be done. You need to set an alarm, right? When you set this distance, you set an alarm. And then you need to find the next alarm and then set another distance, right? I should have set this distance too. And set an alarm, right? This is what's happening. So these are the actions of the algorithm. Setting an alarm and setting a distance and processing a node. So those are all that happens. Okay? Add an alarm, reset the distance, and so on. Okay? And reset the alarm. So there's a few things that happen in this code or these events. What are these events? You set an alarm, you set a distance, and you can reset an alarm, right? Because the original alarm for B was 30, and I lowered it to 24. Okay? So those are the actions, okay, of this algorithm. So now, how do we implement it? Okay, repeat until there are no more alarms. The next alarm goes off at time t for node u. Then the distance from S to u is t, and so on. So this is the algorithm. So this is the interesting step here, right? When you wake up, you process all your neighbors, and you set alarms for them if they're already not processed. If you have you found a better distance to them. Okay? This is the reset. So the implementation is you may need to decrease the alarm for a node. We saw that for node B. And you need to find the next alarm time. Those are the two things, your data structure. Now we're talking about data structures and the priority queue. Okay? So we need to insert a V, a node, a vertex, with a key, a value, its current distance label. That's one thing we need to do. That's setting an alarm. Okay? We need a decrease key. We may need to decrease the alarm value. We see the value for D was 30. When we saw it again, we wanted to set the alarm to 24. Okay? And then we want to delete min, the queue that returns V with the minimum key. Right? That's what we want to do. So those are the three operations in our data structure. Okay? So now we have a data structure that does this. We can rewrite this code where we're inserting in the queue. Now this queue is slightly different than the previous queue. It's a priority queue, right? You can insert things into it with a label, 0 in this case. Then we delete something from it, and now for each edge, we're processing the incident edges to this node U, which we pulled out of the priority queue, which was the one with the minimum valued key. Okay, so we pulled it out of the queue and we removed it from the queue. That's why we got the minimum value and we deleted it, so it's no longer in the queue. And now, now for each edge, if the distance to V, to the node V, is the current label is larger than the D of U plus the length of this edge to that V, now we found a new shortest path, right? The shortest path to U is D of U, and there must be a path. Now you have an edge from U to V, so the length of the path through U is D of U plus L of U V. And that's shorter than the old label you had. Okay? And then, so therefore you set it. This is the notion of, again, vertex B. It was set at 30 because there's a length of edge 30 from the source. And then when you saw C, you saw a better path of length 23 or 24. Okay? And then you put it in the queue again. Or you insert or decrease key. Yeah, so this, if it's not already in the queue, you put it in the queue. You set all the original distances to infinity. So this thing sort of replaces the visited flag. Okay, now what's the runtime? Again, with these graph algorithms, we just sort of see how much we process. Here we process each vertex once, right? Because each vertex is taken out of the queue once. Okay? That's the property of breadth first search. We already proved it. Every level is taking out, every distance d node is taken out, and then only the distance d plus 1 nodes. We're simulating that algorithm. Okay? So each real vertex here, only real vertices are taken out, and each one of those is taken out once. Okay? So there's v delete mins. And now for each vertex, what you do is you process this adjacency list. Okay? There's the most v inserts because you only insert it once, but that's nothing. But there's less than or equal to e decreased keys. This loop, how much time is it for each edge? How much total time is spent in this loop? Well, over all the edges, it's really the size of all the vertices. All the vertices, it's the size of their adjacency list, and we know the size of that is 2 times e. So this should be 2 times e. It shouldn't be 2 times e because you're only going to discover it from one edge first. But in some sense, you're not this. You can do e is the right answer, but let's just be rough and say you process all the adjacency lists as 2 times e. Okay, so now we can do a binary heap, and a binary heap can implement all these operations in log v time, and so the total time is order v plus e. Okay, times log v. Okay, so that's that, and I'm going to show you this binary heap, or even a better one. Okay. Okay, so it's there's another on Friday. I'll give you another proof for Dijkstra, which is just induction, uses an induction. But here it's just really let's simulate breadth first search without actually paying all the costs of on the exploded graph, on this huge exploded graph, without paying all the cost using a priority queue. Okay? Okay, so what is the heap? It looks like this. Okay, so this is the idea. Okay, at every node is 11 is no bigger than 15 and 11, right? If you look at every vertex in here, its children are at least as big as it is. Okay, so 9 is not bigger than 11 and 10. Okay. Okay, so, but do you see a problem in the heap? Yeah, it's in red. That's sort of a hint. Right? You see a problem where it doesn't obey the heap property? Okay, so what can you do to fix it? So that's what we're doing. What we're doing is we're assuming that we had a heap here. Before we put in the 7, this was a heap. Okay, so now I'm going to go over all the operations. How do we insert? So the first thing we do is we just find an empty leaf, a node with a child that we can put it in, and we put 7 there. Okay, so now it doesn't obey the heap property. But what can we do is we can switch it with its parent, right? We know that this guy is if there's a problem here, he's less than his parent, so he just switches places with his parent. Now, do we know that he's less than this guy? Do we have to check? No, because we know this guy is bigger than the parent, and we know this guy is smaller than the parent, so this guy is smaller than this guy. So we don't even need to check. So you just bubble up, right? You just bubble up, you check your parent, you swap, right? Really very easy algorithm. And then you stop. Okay? Now the time of that is just the depth, right? Every time when you swap, you decrease your depth by 1. Okay? Okay, so now delete min. How do you delete min? Where's the min? At the top. So I deleted it. This is a problem, right? This is not even a tree anymore. Right? So how do I fix it? Well, I just grab a leaf, I throw it at the root. Okay. Does this obey the heap property? No. Okay, so what do? I check either my children. I check both my children. If they were both bigger than me, I could stop. right? It would obey the heap property. The only problem is this guy. Everywhere else it was good before. Throwing this guy at the top doesn't, it's a very local condition, right? The only problem is at this new node. So we see that 10 is a disaster. It's both its children are smaller than it. So it picks one, and it goes that way. It picks the smallest one. Okay? Why does it pick the smallest one? What if it went the other way? Then the 7 would be bigger than the 5, and that would be another problem. We don't want to make more problems, right? We have enough. Okay? So we go pick the smallest child, and we switch, and then we pick the smallest child, and we switch. Okay? And now we've done the heap. So this is I'm doing something not big O here, because what I had to do on the way down is I had to look at both of my children and pick the smallest one to switch with. Okay? So that's 2 times the depth. And the reason I'm using the 2 is because later we're going to talk about trees that are not binary. Okay? And then it would be the degree of the tree times the depth. Okay? Okay. So the D area heap is if your degree is D, I'm going to talk about it later, like right now, is the degree is D, what's the depth? Instead of the depth being log base 2 of n, right? It's going to be log base D of n. Okay? Now insert a decreased key. Now it's going to just be the depth, right? We only had to look at our parent. We didn't have to look at the other siblings, right? When we've had a problem, when we decreased the key of a vertex, it might now be smaller than its parent, so it switches with its parent. Okay? And now, if it was smaller than its parent, it's smaller than the other children because it's, the parent was smaller than the other children already. So we didn't need to check the other children. Okay? So the log n over log d is exactly the depth. This is just, you remember your rules of log base d of n is also log n over log d. That's the depth of the tree. Delete min, now this takes more work, right? Because on the way down, you have to look at all your children and only swap with the smallest child. So if the degree is D, you have to scan over all your children and find the smallest one. Okay? So that one has this extra factor of D, but it's still only the depth, log n over log D. Okay? Because you have to check all your children. So Dijkstra is order V delete mins, and each one of these costs D log n over log D. And it's order E, insert and decrease keys. Okay, so you're doing more decrease keys, right? Because you have more edges typically than you have vertices. Okay, so this is why you can do this trade-off. Like it's more for a deeper tree, for a larger degree tree, the D here is bad for the delete mins to make a larger degree tree, because you have to check all your children. You have to do more work. And you get a little bit of benefit from the depth, but, D over log D is always bigger than 1, right? And so, but on the other hand, for going up, it only helps to have larger degree, okay? So if you have a lot more edges than you have vertices, then you want to have a high degree binary heap, because you're going to do a lot more edge operations than you do vertice operations. Okay, so there's a trade-off. This is the thing, and then with some work you can figure out the optimal choice. The optimal choice is to balance these two expressions to set them equal, and if you do that, the optimal choice is for the degree of the binary tree is exactly the average, is roughly the average degree of the graph, which is kind of funny, right? That the data structure is optimized exactly for the average degree of the graph. Okay, the binary tree you should use in your data structure should be around the same degree as the typical degree of a vertex. So it's kind of cute that falls out as the optimal one. Okay, so this is what you get, and then the size of E times log n over log D. Okay, for dense graphs, this approach is linear, right? If E is sort of V squared, this approach is linear. Okay, then there's these fancy heaps called Fibonacci heaps. And they work a little better, and what you can do is you can get some advantage where typically the decreased key doesn't bubble up very far. Okay, so we do some crazy things. It's a crazy thing, maybe, but that data structure you can get it, so it's v log v plus c. So it's linear in the number of edges and pretty efficient in the number of vertices. Okay, almost linear. Okay, so it's linear. It's also linear for monoreal. Okay, so lecture in a minute. Okay, breadth first search, Q's. It sort of organizes the levels into time, 0, 1, D plus 1. Dijkstra, one way to see that is just do breadth first search, but don't do any work on the middle nodes, right? Wait till something interesting happens. Okay, and that's the priority queue, and we saw that. Okay? Okay, so we'll see you on Friday. The binary tree, the heap. You can make a D area.